In this presentation, we'll discuss the unit step signal and its importance in composing many other signals. First, let's recall what the unit step is. A unit step is a signal that's 1 for time greater than 0 and 0 for time less than 0. Now, the unit step, of course, is a causal signal, but it's not everlasting. It's very important for composing other signals, more complex signals, and we'll look at several examples in this lecture. The first one is the causal sign signal. We've seen this before. We take sine of t and we multiply it by the unit step. For time less than 0, the unit step will remove the sine signal and make it 0. But for time greater than 0, the unit step will be 1, and therefore sine of t will appear as before. Another example we looked at was a rectangular pulse signal. We saw a rectangular pulse signal when we were looking at basis functions. A rectangular pulse signal that I'm showing here is 0 for time less than 1, it's 1 between time 1 and time 2, and it's 0 for time greater than 2. We'll show how to compose this rectangular pulse signal from unit step. This can be achieved by subtracting a unit step that has been delayed 2 seconds from a unit step that has been delayed 1 second. At the top you see the signal x. This is our pulse signal. The next signal below this is a unit step that's been delayed by 1 second. And below that is a unit step that's been delayed by 2 seconds. If we subtract the last signal from the second signal, we will get the first signal x. Our next example looks at composing a much more complex signal. This is a trapezoidal profile that's often used in motion control applications for the velocity. You see, during the first second we have constant acceleration. In the next segment, between 1 and 5 seconds, we'd have constant velocity. And between 5 and 6 seconds, we have constant deceleration. So let's take this signal x and we'll break it up into 3 parts: x1, x2, and x3. And I think you can see that by adding x1, x2, and x3, we'll compose the signal x. So our task now is to figure out how to make x1, x2, and x3 by using unit step signals. Now, from the previous example, you probably have a good idea how to compose x2 from unit step signals. But what about x1 and x3? These look a bit more complicated. Let's take a look at x1 first. We'll take advantage of the fact that u of t minus u of t minus 1 is a pulse signal that has value 1 between 0 and 1 second, and 0 before time 0, and 0 after time 1. So when we multiply that term in the square brackets by t, we'll get the triangular signal that is x1. Now we'll turn our attention to x2. It's pretty obvious that x2 is u of t minus 1 minus u of t minus 5, by the exact same logic by which we composed the pulse signal before. What about signal x3? x3 is a delayed version of the signal shown here, x4. It has been delayed by 5 seconds. You see that x4 starts at time 0 and ends at time 1. Once we delay it 5 seconds, it will start at time 5 and end at time 6, in the exact same way as x3. So what is x4? x4 will be 1 minus t times the pulse, u of t minus u of t minus 1. As we saw before, the pulse takes the signal outside of the range 0, 1 and makes it 0. So between 0 and 1 it has a value of 1 minus t, and outside that range it has a value of 0. So we found the mathematical equation for x4. We now need to find out what the equation is for x3. Now recall that x3 is a version of x4 that's been delayed by 5 seconds. And remember that to perform a delay, we simply need to replace t by t minus cap t, where cap t is the delay, in this case 5. So now we'll carry out this mathematical derivation. I have x4 here. It's 1 minus t times quantity u of t minus u of t minus 1, which is the pulse. We're going to delay this by 5 seconds. We'll replace the t by t minus 5, and this will give us x3. So x3 will be 6 minus t times a pulse that starts at time 5 and ends at time 6. That's u of t minus 5 minus u of t minus 6. Now we're ready to make x of t. We simply have to add x1, x2, and x3. And we'll do that here and perform some of the algebra. So we find x of t is t times u of t minus t minus 1 times u of t minus 1 minus t minus 5 times u of t minus 5 minus t minus 6 times u of t minus 6. I'd like you to review the steps we've done. That is how we've composed a trapezoidal velocity profile from unit step signals. Let's now do an example problem where we compose one signal out of another using signal operations. So here's the problem. We're given signal x of t, shown in the upper left, and from it we are to compose signal z of t, shown in the upper right. Now x of t looks like this sawtooth, and z of t is a pulse, and they start and end at different times. What we want to do is to make z out of t only from signal x of t. And the operations we can do to x of t are time compression or expansion, time shifting, and also time reversal. So how do we create z of t from x of t? So we'll create z from x in a series of steps. The first step is I'm going to make a pulse from x of t, and I'll call this pulse x1, and I'll achieve it by adding x of t to a time reversed version of x of t, x of minus t. So let me show first what x of t looks like over here on the left. Then I'll show the time reversed version, and then I'll show the addition of these two signals. So here's x of t, our sawtooth. Here is my time reversed version, and when I add those two together, I'll get a pulse. Perhaps you don't see right now how x of t plus x of minus t creates a pulse, and let me just show you this. Let's find the value of x1 of t at time 1/2. So first I'll find x of t at time 1/2, shown here in green, and then x of minus t at 1/2, here shown in blue, and then for x1 of t at t equals 1/2, I add them together. You see, when we add the values of x of t at t equals 1/2 and the value of x of minus t at t equals 1/2, we'll find that that sum is equal to 1. Now let's try the same thing at t equals minus 1/2. So here's x of t, and plot it over here, and here's x of minus t at that time, plot it over here, and again you can see the sum of x of t and x of minus of t at time t equals 1/2 is equal to 1. And that's true for each and every value of t between -1 and 1. Hence, x1 of t is a pulse. So now we've created a pulse, x1 of t, from the original signal x of t. And what we need to do now is to transform this pulse, x1 of t, into z of t. And you'll note one major difference between these two pulses. x1 of t has a duration of 2 seconds, while z of t has a duration of 4 seconds. So clearly what we need to do is some time expansion. So we'll expand the width by a factor of 2. So here's x2 of t, we write it as x1 of 1/2 t, and when we accomplish that, it'll go between -2 and 2. So now we have the correct width. And we can write that in terms of the original signal. So that'll be x of 1/2 t plus x of minus 1/2 t. So now we've created a pulse signal from our original x of t, and this pulse signal has the same width as z of t. So it's clear we're very close to finished. But there's one more step. Our pulse x2 of t starts at -2 seconds, while z of t starts at -1 second. So what we need to do, obviously, is a time shift. We'll shift x2 rightward by 1 second, and that will then make x2 into z. So that shift, of course, is replacing every t by t minus 1. So z of t is x2 of t minus 1. And that then will be a signal extending between -1 and 3 seconds, our desired result. So we have z of t is x2 of t minus 1, and now let's express that in terms of the original signal, x of t. We found that x2 of t was equal to x of 1/2 t plus x of minus 1/2 t, and z of t is equal to x2 of t minus 1. So now we simply substitute in t minus 1 for each t in x2 of t. So that gives me z of t is x of 1/2 t minus 1 plus x of minus 1/2 t minus 1. And then I can simplify that and write the final answer. It's x of 1/2 t minus 1/2 plus x of minus 1/2 t plus 1/2. And this is our final answer to the problem. Now this is not the only way to create z of t from x of t. In fact, there are an infinite number of ways to do this. And a second possible way is shown at the bottom of the page.